next thing now, says now we have to state the formula that relates the potential difference across a metallic conductor at constant temperature to the current through it. What's that formula? What's the formula? What's the formula here? Huh? Are we still connected?
Sir, I'm not sure, but is it the V is equal to I times R?
Yes. V is equal to IR. So V, which is a potential difference, is equal to the current through the metallic conductor multiplied by the resistance of the metallic conductor. And this formula is for which law in physics?
Sir, Ohm's law.
Ohm's law, absolutely. All right. Next thing it says now state the formula that expresses the total resistance RT of two resistors R1 and R2 in parallel. What we're going to say for this?
R1 over RT equals 1 over R1 plus 1 over R2.
Sorry. Plus 1 over R2. Right? Got to clear with this?
Yes, sir, but sometimes it does have 3.
Yes, yes, but they just want 2, so just for 2. Now, also, once we have two resistors in parallel, right? Two resistors in parallel, we can also write that the total resistance RT is equal to the product of the two resistors over their sum. Okay? But again, only when we have two resistors we can use this. Cool? We can go again. Come on. Nothing from anybody. Anybody connected?
Yes.
Yes? No?
Yes, sir.
Okay. All right, next one. The brightness of the incandescent bulb in figure 4 may be increased by varying the rheostat between 0 and 100 ohms. When lit, the bulb operates at 0.3 amperes and 3 volts. Now the examiner says, what is the resistance of the bulb? How would do that? How will find the resistance of the bulb? Hello? Yes. We can continue.
Yes, sir. Sir, is it R equals V over I?
R is equal to V over I. Okay? So the resistance R is equal to the voltage divided by the current. Alright, from Ohm's law, so V is equal to IR, we're transposed to make R the subject, and we'll get this thing. So R then now is V over I, and they said that V was 3 volts and I is 0.3 amperes. So we're going to say 3 volts divided by 0.3 amperes. So therefore R is what? R is
10
10. 10 what?
amperes. No. Ohms.
Right? 10 ohms. Next one now says that assuming the resistance of the bulb remains constant once lit, calculate the ammeter reading if the rheostat is set at 100 ohms. So we know that this bulb is 10 ohms. We just calculated it a while ago, yes?
Yes, sir.
Now the examiner is telling us that the rheostat is set to 100 ohms, yes?
Yes, sir.
Then he's asking us to tell him, what is he asking us to tell him? What the examiner wants to know.
The resistance remain constant.
And what does the examiner want to know?
So calculate the ammeter. So the ammeter reading. Oh.
The what?
The ammeter reading.
The ammeter reading, right? And the ammeter reading will tell us what?
The current.
The current, okay. The current where?
In the circuit?
In the circuit, right? So what the examiner wants us to do is to calculate the current flowing in the circuit. So how we go about doing that? How we go about doing that?
Sir, I equals V over R.
Okay, V over R. And what's V?
Voltage.
Right, and what's the value?
The value?
Yeah, for the voltage.
100. No. Oh my gosh. Say 3.
3 volts, yes?
Yeah.
And what's the resistance?
10.
10, okay. Everybody agree?
So you could go it over.
Okay, we're just trying to figure out what's going on, you know. We know that I is equal to V over R, but we need to know V, we need to know the value for R. We're saying that V is 3 volts because that's the EMF of the battery, but we need to know R. Now remember, we're trying to find the current flowing in the circuit, right?
Yes, sir.
So R that we will have to use in our calculation must be the resistance of what?
The current.
R must be the resistance of what?
The ammeter.
Alright, go out. No. Let's just take it a moment by moment. We're trying to find the current flowing where?
In the circuit.
In the circuit. So the resistance that we will use must be the resistance of what?
Sir, the bulb.
Again, we're trying to find the current of the circuit.
Voltage.
Hold on a second. We're trying to find the current of the circuit, right? Current in this flowing in the circuit, yes?
Yes, sir.
So we need to know the resistance of what?
The ammeter.
Not the ammeter. Remember, we have the bulb and the rheostat. Hold on a second. We have the bulb and the rheostat connected in our circuit, yes? Is that so?
Yes, sir.
So now, if we need to find the current flowing in the circuit, we have to find the resistance of the entire circuit. Now remember, an ammeter doesn't offer any resistance to the circuit. So the resistance of the circuit will solely be due to the bulb and the rheostat. Agree?
Yes, sir.
So what do we do next?
We'll find the total resistance.
Okay? So first have to find the total resistance, right? So the total resistance, let us say we call that R, right? Or let me just say RT. Let's put it right here. IT, RT. So RT, again, how would you find the total resistance in this case?
Sir, R1 plus RT and continue.
Okay, what type of configuration these two components are connected in?
In a series.
Series, agree? Everybody agree? Where's Kamani? Not hearing from Kamani.
I'm here, sir.
Yes, so help us out now. We're struggling with the thing. Help us out.
Sir, I've been struggling more than everybody right now.
All right. So remember, some time ago, I think I would have mentioned somewhere that when we're looking at circuits, right, and we want to tell if it's series or parallel, just always trace the path of current. So let us say the current leaves from the battery, goes through the switch, goes through the ammeter. Then when it comes to this point, what's going to happen to the current?
Sir, which point?
When the current reaches at this point, what happens to it?
Oh, it's gonna Separate.
It's going to separate, right? In other words, it's going to split. True?
Yes, sir.
Right. Everybody else agree?
Yes, sir.
So once the current splits, right, that simply means then that these two components, they share a parallel connection. Okay? So these two bulbs are actually in parallel. Cool?
Yes, sir.
So if they're in parallel now, two resistors in parallel, remember, we can use the product over sum. So let's just quickly use that one. So product over sum now, so we're going to say, this is all like 10 times 100 divided by 10 plus 100, which is like 1000 divided by 110. Yes? What's this?
I think that's 0.11.
0 point how much?
11.
No, that's one. Like remember it's 1000 divided by 110, you know.
Oh.
Sir, 9.09.
9.09. That's so more like it. 9.9 ohms. So now, to find the total current now, we just simply say IT is equal to V, which is 3 volts, divided by the total resistance of the circuit, which is 9.09 ohms, and this works out to be
0.33.
and the current, is 0.33, so we have to write the unit as what?
Amperes.
Amperes. Right? That's good?
Yes, sir.
Okay. Sarah?
Yes, sir.
Yes. Aisha?
Yes, sir.
Perfect, okay. Next now, it says now that, is there a danger in reducing the rheostat too much? And the examiner wants us to explain. Yeah. Yeah, so what was that about this? What was that about this? Is there a danger in reducing the rheostat too much? By the way, what's the lowest we can reduce the rheostat to?
Sir, 10.
The lowest. Remember, it goes from what? The rheostat goes from. What's the lowest it can go to?
5.
No?
So the resistance?
Oh, let's go again. The brightness of the incandescent bulb in figure 4 may be increased by varying the rheostat between what?
0 ohms and 100 ohms.
0 ohms and 100 ohms, right? So what's the lowest the rheostat can go to?
0.
0 ohms, right? So now, let's say for instance, we reduce this rheostat to 0 ohms, right? If we reduce this to 0 ohms, what it will simply mean is that we would have just have a single piece of wire, right? Just one straight piece of wire from here to here, right? Just one straight piece of wire, okay? With me? All right, let me draw it like how we normally.
So is these questions they're going to really ask in exam, sir?
Yeah. But think about it. It's a fun. It's a fun.
It's going to ask you, sir. Them something here is not for you, man.
It's a fun question. Watch this. You know,
So
it's a
this
fun
is
question.
not fun.
What you're going to say? You're going to say. So we just have a piece of wire like this, right? A piece of wire, because when we reduce this rheostat to 0, as I said, it's like we have a piece of wire, because theoretically, a piece of wire has a resistance of what? Somebody say 0?
Yes, sir. Someone did 0.
Yeah, 0. So I was suggesting that somebody should say 0. So a piece of wire will have a resistance of 0 ohms, yes?
Yes, sir.
Now, once we connect a 0 ohm wire across this right here, which again is due to the rheostat being at 0, okay? So just instead of the rheostat being right here, as I said, we just put a piece of wire. Cool?
Yes, sir.
Right? Now, if that's the case now, what's going to happen is that we're going to set up a very interesting situation right here. Anybody know what's the name for when we connect a 0 ohm, well, we connect a piece of wire across a component, for instance, like this bulb right here? Anybody know the name of that situation that arises?
So repeat again.
Right, so when we connect, let us say we have a circuit and we connect a piece of wire across our component in the circuit. Right, there's a name we give to that type of connection.
So forget it. Let no.
All right, think about it this way. Let's say if we can, make sense of it. Think about like, let us say, let's say let's say when the electron come right here, or the current comes right here. Let's just use the word current. Let us say when the current comes right here, the current has to go through this bulb. But in order for the current to go through the bulb, it takes a lot of energy for it to go through the bulb, right? But if we place a piece of wire now, the current is going to get very excited because if it goes around this wire, it doesn't have to utilize enough or utilize a lot of energy. So in everyday conversation, let us say, there's a path that you have to probably drive through or you have to walk through, but it is always congested, right? But you know of an alternate route. What do you call that alternate route?
So shortcut.
Shortcut, right? So in this case now, it's a similar thing that happens with the current. But instead of a shortcut, we say a short what?
Circuit. Current.
Circuit, short circuit, right? So with this piece of wire right here that has a resistance of 0 ohm due to the rheostat being 0 ohm, we're going to have a short circuit. Yes? Cool?
Yes, sir.
So no current will actually flow through the bulb. That's the first thing. Because of this short circuit right here, as I said, the current has an easy path. So it's just going to go through here instead of going through the bulb. So the first thing that will happen is that this bulb, it will not glow.
Wait, sir, I think your screen froze because I'm looking and I'm not seeing anything.
All right, what are you saying now? Is
Sir,
it?
I'm seeing it now, you just slide.
Okay, right. So what I'm saying now is that with this piece of wire right here, or due to the rheostat being 0 ohm, we're going to get a short circuit. Now that short circuit will cause,
Sir, sir, you're pointing on something?
yes.
Sir, I'm not seeing that.
Can you see the writing?
Sir, I'm seeing it now.
Yeah, I think when I move the cursor, it doesn't. Do I have a highlight thing?
There's no pointer, sir. You see the
Yeah.
cursor.
Yeah, that's the
So,
thing. Yeah, there's no cursor. So let's continue. So with the black line, right? Watch the black line. So the current is just gonna go around this black line, right? So no current flows here, right? So no current flows through here, through the bulb, right? With me?
yes, sir.
Right, so no current flows here. So let's put the X across there, no current flows through, right? So that will ensure that the bulb does not glow. That's the first thing. So the bulb does not glow. Cool?
Yes, sir.
Right? So that's the first thing that happens, right, due to the short circuit. So as I said, when we reduce the rheostat to 0, we're going to set up what is called a short circuit. And that will cause the bulb to not glow. But at the same time, what we're going to have is we're going to have an excess current flowing in the circuit. Because remember, I is equal to V over R. And V is 3 volts and R is 0 ohms. What's 3 divided by 0? Somebody say infinity
Zero.
or undefined?
Yeah, undefined.
Yeah?
Max.
Right. Yeah, it's undefined because it is infinity. We know infinity, we cannot measure infinity. It's just a concept. Right? So 3 divided by 0 is undefined. So therefore now the current flowing in this will be so large that it's going to cause the circuit to burn up. See that?
Yes, sir.
Right? So fun it was, Chrisan?
Sir, no.
Yeah, but it's a very, very, very interesting question. I mean, it allows us to kind of, think and see what really going to happen. But as I said, the main thing is that when you bring this to 0, you're going to have a short circuit. So the bulb will not glow and the circuit will heat up and probably even burn up because of the high current that flows. So let me put that in words then now. So what we can say now is that the rheostat being at 0 ohms being at 0 ohms will cause a short circuit, right? This results in the bulb being off, this will result in the bulb not turning on, and also cause a very large current to flow, which causes the circuit to heat up, right, and possibly cause a fire, right, possibly. So we want to tell the examiner that, we know what's going to happen, right, possibly cause a fire. Okay, Sarah?
Yes, sir.
It's good, cover on.
Sir?
That's good?
Yes, sir.
Okay. Now, it says now that the assumption made in B2 is incorrect. With the, let me see this question. The assumption made in B2 is incorrect. With the aid of IV graph, indicate how the bulb resistance varies with current. Okay, the assumption in B2. Okay, I thought they were talking about our assumption here. Because that would be kind of strange. But, what they're saying right here, let's kind of just observe what they're saying. They're saying that the assumption made in B2 is incorrect, which is this assumption right here, right? That the resistance remains constant. But for a bulb, that does not happen because, anybody remember anything about Ohm's law? Other than the formula? Yes, no?
Sir, the current is directly proportional to something. Forgot. To the resistance.
Not the resistance, to the potential difference.
Oh,
Right? But under a specific condition.
when temperature is constant.
Right, temperature must be constant. But what you will realize is that when you turn on a bulb, does the temperature remain constant?
No, sir.
Exactly, the temperature changes. So therefore now, because the temperature changes, the resistance will also change. So now, when we plot a graph of current against voltage for a bulb, right, we're going to get something looking like this. So
A straight line.
no, not a straight line because it's not constant. Well, we're going to get a straight line for a small section, right? But as soon as the bulb starts to heat up, we're going to see something different. Hold on a second. Let me just do it in one thing. So we're going to have current against voltage. So this is voltage right here, current. So what we're going to see is we're going to have the current and the voltage increasing like this up to a point. Then we're going to see it go like that. Okay?
Oh, okay.
Right, so this is the IV characteristic for a filament lamp or a bulb. I was going to draw it in the negative as well, and we're going to see a similar thing. So if we also draw the negative axis, we'll get something similar. So it would actually go like this, so right? Something like that. I mean, I run out of space, so forgive me, right? But just as we see it in this direction, in the positive direction, we're also going to see it in the negative direction. Okay? So we're going to see that the current and the voltage are going to be almost proportional to each other until once the bulb heats up, it's going to change. Cool? Shall we continue?
Yes, sir.
Yes,
Yes,
sir.
sir.
All right, so